Good morning, everyone. Greetings from the Department of Mechanical Engineering, Jyoti Engineering College. It gives me immense pleasure to welcome you all to the second day of the online faculty development program on solar energy technologies and applications, organized by the Department of Mechanical Engineering, Jyoti Engineering College, Thrissur, sponsored by AICTE Training and Learning, ATAL Academy, New Delhi. Indeed, it's of great happiness to have with us Dr. Nazmul Ahsan to lead the fourth session. Dr. Nazmul Ahsan received the Bachelor of Engineering in Electrical and Electronic Information Engineering from Toyohashi University of Technology, Japan in 1997, the MS and PhD degrees in Electronic Engineering from the University of Tokyo, Japan in 1999 and 2002 respectively. He is currently a research associate professor at the Research Center for Advanced Science and Technology RCAST of the University of Tokyo. His research interests include ultra-high efficiency photovoltaic devices, spintronic devices, molecular beam epitaxy of compound semiconductors, material design and characterization. Dr. Ahsan is a member of the IEEE, the Japan Society of Applied Physics (JSAP), and the American Physical Society (APS). In 2020, he has been named as Fellow of International Association of Advanced Materials for contribution to strengthening the advancement of materials. He has been serving as a PI and co-PI of several government and international funded projects and published around 100 scientific articles. On behalf of the Department of Mechanical Engineering, Jyoti Engineering College, we extend our heartiest welcome to you, sir, and wishing all the participants a wonderful and great session ahead.
Okay, so thank you very much for the nice introduction. So can I continue?
Yes, sir. Please proceed, sir.
Okay. So thank you very much for giving me an opportunity to talk in front of audiences. And I hope you are all okay, in good health in this very difficult time of Corona. And I believe you are getting used to this new environment. And today I'm going to talk about the materials and device engineering for the next generation solar cells. So at the very beginning, I'm going to give a little introduction where I'm working right now, and then I'm going to talk about what exactly I'm talking about, wish to talk the next generation of solar cells. Okay, so first thing first, currently, as I was introduced, that I work in the University of Tokyo in this Research Center for Advanced Science and Technology. And there we work in the advanced device and new ideas. So before going further, let me introduce the location of my institute. So if I think it will be difficult for you to see, because this is written in white font and also in Japanese right here. So here I have written OurCast. So this is the Research Center for Advanced Science and Technology of University of Tokyo. So the Tokyo University has a couple of campuses, and it is right in the center of Tokyo, but we have a couple of campuses. One campus is very close to this green area. If you look at the green area, you can't see any green area, in fact, except our campus, because Tokyo is highly dense area. So this is our campus, we call Komaba campus. And if you see a couple of buildings right here, so this is our cast. Okay, and if we go down there, we have so this camp. Okay, right here, this campus for graduate students and researchers. So only PhD student can enroll in our institute. But if you go a couple of few hundred meters away, we have another campus. I cannot show you right here, but the green area here show that okay, some green area on the right side, and that is we have another campus, and there we have the another campus for the undergrad students. Okay, and now if you see that there are couple pretty much skyscrapers on the center, and okay, so this building right here, this is the building. I think this is 60 stories, something like that. I cannot remember what exactly how high it is, but the mayor of Tokyo, he has his office in this building. And so this is the center, and in Tokyo is mainly a metropolitan of train stations. So right here around we have Shinjuku station, and from there I think the distance is a few kilometers. And in Corona, the okay, in Japan, we had the highest concern in this area, because here was the maximum number of the Corona positive people reported. So we are pretty much careful about the and watchful about the situation going there. And still now our campus, we are okay. We have very limited access to the campus, and mostly we take our lectures online. Not mostly, it's 100%. We had last spring semester, all the lectures we take online, and this autumn semester, starting soon, it will continue again online. Okay, so with this background, let me continue. Okay, so now let me, this is the introduction of what I'm going to talk today. But before that, this is a very popular chart. Okay, this is the chart of the best research cell efficiencies in the world. Okay, and this data, if you guys go to the NREL site, I have written the reference there. This is the National Renewable Energy Laboratory in the United States. And this is very popular because this chart bring down all the world record solar cell efficiencies on this chart. And the interesting thing with this chart that the data, each point here is a data, and this data is not the data which are only published in any scientific journal. These are the data who has to pass through very specific testing in some three testing facilities in the world. And so if somebody want to claim that they have very good solar cell efficiency, and that is not sufficient to come into plot here, you have to give very specific solar cell device to three agencies. It could be either NREL, United States, or AIST, Japan, and Fraunhofer in the Germany. So any of the three institute, okay, they can take the, they have the facilities to test your solar cell, but with specific conditions. And all the data you can see, they have passed through this very difficult test. And you can trust the data. Okay, so what is the data talking about? If you look at the horizontal axis, this is a year. And right here, 1975. And today we are sitting 2020. So, so this is the point right here is 2020. And the vertical axis is the efficiency of solar cells. So, okay, so I think I should, because this is, I know the audience are sitting right there. They're from different background, but just let me be, I'll be talking about what exactly is this efficiency we are talking about. And based on that, I'm gonna introduce you some new ideas for next generation solar cells. Okay, so the first thing first, okay, here this efficiency, if you look at there, this is 0 efficiency, and right here 50, and there is a theoretical principle we call detail balance principle, and based on the thermodynamics, so theoretical limit. And if you have a solar cell, because you know the solar cell is a sandwich of 2 semiconductor, p-type semiconductor and n-type semiconductor. This is a sandwich of 2 material, and one sandwich we call a single junction. Okay, so and if you look at this, I have drawn this pink dotted line. If you see there, maybe difficult in your eyes because so many dotted lines, but just look at here, this pink dotted line, and this is the theoretical limit. Okay, and because the paper was published by Shockley and Quasar, Shockley, he's very famous in semiconductor, and also so they have published a paper. I think it was published in 1971 or 2, and so by their name, and the limit says 31%. So what exactly is 31%? This is the theoretical limit. You cannot break. No matter how best semiconductor you make a PN junction, you never can, because this is theoretical limit. You can only go, okay, beyond this, not beyond this. You never can go beyond, only less than this, okay. So most of the data you see is below this limit. And again, what exactly is this efficiency, okay? So, okay, if it is 100% means all the solar energy coming from the sunlight, okay, if you can convert it to electrical energy, if it is 100%, it is not possible, but let's assume that you can convert all the energy from the sun, solar energy to electrical energy, then it is 100%. Okay, but this theory says that you never can break 31% limit, or let's say around 30%. So it also says that no matter what, okay, you can only convert 30% or 31% anyway, around 30% of the solar energy to electrical energy, and it also means the 70% will be lost no matter what. Okay, so this put a limit, theoretical limit. Okay, you can only approach that, but you cannot break it. So this is theoretical limit, by the way. So this efficiency is that, okay, the efficiency, this tells, okay, how much you convert solar energy to electrical energy. Okay, if you can't convert anything, this is 0%. Okay, if you can convert more and more, it just goes high on the scale. And just look at once, I'm gonna come to this 30% again, because I told you this is theoretical limit, we cannot break it, but still you see that there are a lot of data which are breaking the limit very recently, since 2000. You see, we started to see before 2000, this is the year 2000, okay? Before 2000, you see nobody could break this limit, but suddenly after 2000, okay, we could break it, and we are continuing to break it, and we are going toward 50%. And in our laboratory, in our research, we want to break this 50% and go beyond, because you guy knows that the more you can convert solar energy to electrical energy, you can reduce the cost of the solar energy, and we want to compete with the fossil fuels, because the global warming is the huge concern these days. So fossil fuels, you have to reduce the amount of the use of the fossil fuels. But the point is, if we cannot reduce the cost, okay, people cannot afford to use solar cells. So main target is to reduce the cost. And okay, for example, for example, the silicon. Look at okay, it is difficult for you guys to see so many points. Just I think easy to look at this. Okay, look at this blue square. Okay, look at this blue square. What is so? Each color means different material. And today the talk I started that materials and device engineering. Okay, Okay, when I say materials, mean there are different materials in semiconductor. Let's say silicon is very popular material, and this blue one is the silicon solar cell. Okay, this blue is the silicon solar cell. But these days, okay, for example, probably you have heard perovskite solar cell. Okay, and for example, the perovskite is this yellow, I think. Okay, this yellow by this red circle. Okay. And if you look at here, this is a perovskite solar cell. Okay. Okay. And there are different kind of materials and all written here, but I'm going to introduce because this is a motivational and I have given so long time today. Okay. And we have, so I think I should be a little slow and give enough foundation to understand what I want to talk about. Okay. So let's silicon. Okay. We here in this chart, silicon started to appear from 1976, but the world first silicon solar cell was in reported in the Wells lab in 1954. Okay, and that was around 5%. Okay, but you know, but this chart started from 1976. Okay, so but in 1976, silicon solar cell was very close to 13%. And they started silicon going higher and higher, okay? And there are different companies or research institute, for example, this data from Mobile Solar, then RCA, then Sandia, and Westinghouse, and going there, and this is UNSW in Australia. And this Stanford University come here. Then again, so each point, and it has who are the institute or industry or the university reporting the data. Okay, and this data, okay, so Green, Professor Green, he has done a very good job in the solar silicon solar cells. So you see most often come New South Wales, University of New South Wales in Australia, and they appear pretty okay a couple of times right here. So, and then Stanford come here, and UNSW come here, UNSW come here, and if you go there, so far from 1976 to 1995, it was all happy news, good news, going higher and higher and higher. But again, I remind you that you never can break this 31% limit. I'm going to talk about this later, okay? But you cannot break it. This is theoretical limit. Why you cannot break it and how to break it, this is the purpose of today's talk. So, okay, it tells we cannot break it, but today I'm going to talk about what are the tricks we can break it, okay? And, okay, but, okay, and since 1995 now, you start to see that there is not much good news. Okay, let's say in 2000, it was UNSW reported, and then there is no new report coming, and it's a flat line, all through flat line. Okay, and it could not go closer to the Shockley-Quasar limit, and the conversion efficiency was 25.6%. Okay, so in silicon solar cell, okay, this is 25.6%. This is the world record. Okay, but for silicon, what I'm talking about, okay, there are two types of technology. One technology is just under one sun, but there are new ideas. You can concentrate the sunlight. Okay, you can concentrate by cheap materials, plastics, like the magnifying glass. And you can reduce the cost of the semiconductor, because, you know, having a good semiconductor, it is very hard job. And right during the Second World War, it was only Bell Labs guys who made high quality semiconductor, and there are a lot of discoveries since then. But it is very expensive to have a very high quality semiconductor. So one, to reduce the cost, okay, we people have brought new ideas of concentration, that why don't we concentrate the sunlight by something and put your expensive PN junction solar cell, small piece of PN junction somewhere down, and then you could convert electricity. And in fact, this is very tricky, and this is very, and theoretically, it gives more conversion efficiency, okay? Okay, if you concentrate the sunlight, okay, it will give you more efficiency. Okay, that's why you started to sum up the point. Okay, right here, dotted line. They are also blue because I told you these blues are all about silicon solar cell. Okay, okay. So the field square blue is single junction PN solar cell. I mean non-concentrator. But if you concentrate the sunlight and the same solar cell, okay, will show you higher efficiency. So you have two advantages. If you have a concentrating system, that you can reduce the cost of the semiconductor, okay, because you are using cost-effective materials instead of semiconductor. And second, you are increasing the efficiency. So you have, okay, a double benefit when you use concentration. And okay, for example, this company, SunPower, they have concentrated the sunlight 96 times and they have a higher efficiency, okay? But yet you never can break this 31%, okay? This is theoretical limit. And there is another company, this is French company, and they have also 27.6% solar conversion efficiency in silicon, but under concentration. So I just introduced you non-concentrating solar cell, silicon, single junction, and they have been so flat, but you have some point right here which are under concentration. Okay, so so this is silicon solar cell, but you guys might ask me, look, when you go to the market, you buy the panel, silicon panel, the efficiency is not close to 25, 26. They're less than 20% because those are panel. If you look at the title right here, research cell efficiency. When you talk about cell, these are very small piece of semiconductor, but when you put them in a big panel, then it's not only solar cell semiconductor. You have other, let's say wiring. You have other shadowing, other problems in your whole panels. Okay. And you have heating issues, so many things. And these all things only bring down your efficiency down to 20% or less, okay? So, okay, so when we talk about panels, you have other issues coming together. But at the core of the heart, it's all about the cell, okay? Okay, and now, okay, I just told you that in 1954, the silicon solar cell efficiency was 5%. And today, the efficiency, let's say in the best case, 27.6%. So if you do easy mathematics, from 5% to 27%, it's around, let's say, close to 22 or 23% in more than close to 70 years. In close to 70 years, we could, okay, just bring 50%, 5% to 27%. But then new materials. So, for example, this perovskite. These guys started somewhere around 2000. Okay. So, yeah. Okay, and very interesting here. These are emerging photovoltaics. So, okay. So if you look at this group of material, these are called emerging photovoltaics. Okay, and one of the points is quantum dot solar cell. And this is also one of the material. Today I will not cover, but we also working on this. Also, there are other materials, CZT, SCC, okay, or CIGS. Okay, today, and okay, so the green are CIGS solar cell. These are thin film solar cell, and these are called second generation solar cell. Okay, so so just I quickly used one word. Okay, second generation solar cell. So first generation solar cell are the silicon solar cell. Okay. Okay, you don't care about cost. First generation, you don't care about cost. You care about efficiency, and it's very expensive, but you want to go closer to the theoretical limit. These are first generation solar cell. Okay, good news, you can convert high amount of photovoltaics, solar energy to electrical energy, but the bad news was is very expensive because these are high quality semiconductor. And then the second generation solar cell, let's say this green point, these are CIGS solar cell now we know that theoretical we can go closer to theoretical limit. Why don't you reduce the cost? And to do that, to reduce the cost, obviously you have to reduce the material cost. To do that, and we cannot play with the area, because we can work with the area if you have concentrate, but forget about concentrating solar cell. Let's say sunlight, you are given the energy by the area. Okay, you have not hand on that. For example, the energy coming from the sunlight is 1 kilowatt per square meter. Okay, if you're given 1 square meter on your rooftop, you are getting 1 kilowatt. Okay, you have no way. This is the limit. Okay, or 1 milliwatt per centimeter square. Okay, 1 watt per centimeter square, or 1 kilowatt per meter square. So I think I'm missing 100 milliwatt per square centimeter. Okay, 100 milliwatt per square centimeter. But easy to remember, 1 kilowatt per let's say 1 meter square. I'm using meter because that's I'm used to. I'm not using feet or square feet. Okay. Okay, now this second generation guy says that, look, we cannot work with the area, but you can reduce the thickness of the material. Effectively, you are reducing the volume. So these are called, the second generation solar cell are called thin film solar cell. But to reduce the thickness, it's not an easy job, because the principle of solar cell, I'm going to introduce again, that you have to absorb the sunlight. And if it is too thin, you cannot absorb all the sunlight. So yeah, if from sunlight point of view, if you have a very, very thick material, or technically you have a very high volume of semiconductor, then you can absorb all the solar light. But if your material is thin, okay, most of the light will be passing through, and from the sunlight, it will be transparent, okay. But the idea is here that, okay, so if we can make thin semiconductor material who has very high absorption coefficient, then we can reduce the thickness, and these are thin film solar cells, okay. Let's say this CIGS solar cell, okay. So but yet so they're very cost effective, by the way. These are very cheap compared to silicon single junction solar, single crystalline solar cell. And as you see, they're going high and high and high and high, and okay. And right now the world record of CIGS solar cell from CIGS, okay, from Solar Frontier. The name has changed very recently because this company is bought by Shell. This is a Japanese company, Solar Frontier. But you will not see the name right now because it is bought by Shell. And they made a very good world record is 23.3%. To be right, 23.35% in their paper they published, but here 23.3. Okay, so so these are, I'm talking about green point. I already talked about the perovskite, okay, and there are some quantum dot solar cell, okay, coming here, and there are other materials, okay, but I should again now go to this part, okay, because I told you that it is very difficult to break this Shockley quasar limit. Out of 100 photon energy coming from the sun, only you can convert 30% or 31%. That's so sad, okay? We want to break it. And only we want to break it for different purpose. One purpose, the loss, we are missing the 70% loss, they convert mainly to heat. And the bad side, if you heat your semiconductor or material, you reduce the efficiency more and more, okay? So heating, okay? So to improve the solar cell efficiency, okay, you have to cool down your solar cell, okay? But the 70% loss will heat your semiconductor material. It's just kind of trouble. So we want to reduce the heating, or otherwise we want to improve the efficiency, and all this good news then. And now there are new concept or new solar cell right here, and this, okay, I think I heard something. I'm taking a little bit long time here because I'm given long talk time. Okay, so these are multi-junction solar cell. Okay, right here, multi-junction solar cell. I'm going to talk about multi-junction solar cell and how come they can break the limit. And based on that, I'm going to talk about the ideas we are working in our laboratory. Okay, so today I already talked about that there are new junction, okay, multi-junction solar cell, and the world record right now is 46%, and this is okay. This is okay. This is 4-junction solar cell. So you have 4 PN junction in series. Okay. So far these are just single piece of PN junction. Single piece of PN junction. But if you have 2 junction, 3 junction, 4 junction, you can break this limit. This is called multi-junction solar cell, and this is what we are working here. But today I'm going to go a little bit beyond, because multi-junction solar cell demonstrated that they could break the theoretical limit and go. They're approaching 50%, but they're very expensive. Multi-junction solar cell right now we are using for the satellite, okay, to power the satellite. But to use for the terrestrial purpose, they're very expensive. So new ideas were working, but in parallel, we are trying. Do you have any cost-effective ideas to break this multi-junction, substitute this multi-junction idea? And this is the motivation here, that intermediate bandgap solar cells. Okay, and I'm going to talk about here today. So this solar cell is not reported yet, because this is a new idea. Some of the working we are doing, so it didn't appear in the chart. Okay, some of the people are working on it, including us, and this is the cost-effective alternative to multi-junction solar cell. Okay, and I'm going to talk about here more details, and just here, let's say if you have this is a very simple concept. If you have a single intermediate band in a single piece of semiconductor, because multi-junction you need to bring multiple PN junction and different semiconductor. For example, the world record people made for 3 junction. For that you need to bring germanium PN junction, and on top you have to bring gallium indium arsenide PN junction, and on top you have to bring gallium indium phosphide, and these are all very expensive compound semiconductor, and you have to make them lattice match, and this is more difficult technology, and this makes more expensive. But here the intermediate bandgap solar cell is a little bit easy ideas, that you have a single piece of semiconductor. Don't bring many semiconductor. Rather, in a semiconductor, we know we have a band gap, and put a intermediate band in between. Then in theory, we can make 63% of conversion efficiency just with a single intermediate band between the band gap. And that's the motivation of the ideas. And there are different materials I'm talking about. For example, 3,5 gallium arsenide based idea. And this is, we use molecular beam epitaxy. And there's another idea. I just talked about CIGS solar cell. And based on that idea, we have 136 chalcopyrite materials. And this material, set of materials, we use radio frequency sputtering. And we have different ideas in device design and engineering, and different issues of the, let's say, thermal escape of the photoelectron, then tunneling leakage of the electron from your semiconductor to the contact, and the key to this idea is 2 photon absorption. Okay, for the intermediate band gap, let's say if you don't have intermediate band gap, okay, most of the photon will pass through your material. But if you have some band in between, then you can absorb the long wavelength photons. Okay, and you convert these photons to a single photon by 2 photon absorption, and that is the key for the 63% efficiency. And I'm trying to explain what exactly is this intermediate band gap here. And before going there, I'm showing you a schematic diagram. What exactly is multi-junction solar cell? So I told you that our target is to go beyond 50% conversion efficiency. And in our lab, we are working in 2 different ways. One is multi-junction solar cell, and this is intermediate band solar cell. But multi-junction solar cell is already proved they are very potential, and they have world record of 47%. And this is the idea, that this is a schematic picture of the solar photon coming from the sun, okay? And in the horizontal axis, I did not put any number. I have written just wavelength, okay? This is short wavelength, and you go down there, long wavelength, and the vertical axis is the energy, photon energy, okay? You know that each photon has a different color, okay? That's what we see in the rainbow, different kind of colors, okay? And different colors at different wavelength. And in the vertical axis, different color has different energy. So this is the energy, okay? And this part is pretty close to yellow or green, and they have the maximum energy, okay, right here. That's why you see a peak here. And if you go, okay, short kind of wavelength, okay, quickly they fall down, okay. It is because their number is very less in this area. The short wavelength are high energy, but their number, this is not only energy, but also number of how many photons you can collect them. So the point is, in the ozone sphere, you are reflecting most of the ultraviolet rays, so you don't see them here in our, okay. And also from the sunlight, okay, there is not much coming here. And again, if you go down there in the long wavelength area, you see we have many photons here. But if you have a single junction material, okay, in a single semiconductor means single junction means you have a single piece of semiconductor, and in a single piece of semiconductor you have a band gap. Imagine you don't have this kind of things, okay? So in a semiconductor you have valence band states, and you have conduction band states on top, and in between we call forbidden gap, okay? So nothing inside. So in a clean semiconductor, don't imagine this kind of intermediate band gap. This is the ideas I'm putting here. But in a clean material, you have valence band and conduction band. So if you have a single piece of semiconductor, you only can grab only a small part of the whole spectrum, okay? This is the limit of the Shockley quasar limit, 31%, that you have so broad spectrum coming from the sunlight, but because you have a single PN junction, you can only get a very limited spectrum out of the whole sunlight, and that limit you 31%, okay? But if you have multiple piece of PN junction, okay, let's say, okay, let's say germanium have a low band gap material, so you have a different kind of semiconductor PN junction, another semiconductor PN junction, another semiconductor PN junction, then you can split the whole spectrum into different window, and for each window you just assign different piece of semiconductor who are good in that area, okay? So the ideas of multi-junction is, okay, just assign the guy who is good in that area, put him there. Don't keep him busy in rest of the part, okay? Because inefficient in other part, make him efficient where he's good at. And bring. I think I can
Dear participants, please mute your mic.
Thank you so much. Yeah, I thought I was asking some question. Okay, okay, I can continue. So you can assign, you can split the solar spectrum into different window, and you assign different piece of semiconductor into different junction. This is the idea of multi-junction solar cell, and that is why we have the world record efficiency in the multi-junction solar cell. But I told you this is very expensive. But how about a new idea? Let's say we have a single piece of semiconductor and it has a valence band and conduction band state. Okay, it means the sunlight, if it comes here, it can excite the electron from the valence band to the conduction band. But if you have some intermediate band steps in between, then the long wavelength photon who pass through the gap, they can excite electron, okay, from the valence band to this intermediate steps or intermediate band, and another photon can excite this electron to there, and effectively you are reducing the loss of this long wavelength and exciting this electron to there, and you can convert electricity. So intermediate band gaps can help you. So if you look at there, can help you very similar to there. That here you have three different semiconductor with three different band gap, but here you have three band gap due to one single intermediate, because you see one band gap is here, another band gap is there, another band gap here, just due to one single intermediate state, okay, in between, you are generating 3 band gaps, and this is the ideas. And the question then comes how you make this intermediate step, and this is the challenging technology, how we can make this kind of gap, okay? But if you can do that, it is very similar to a 3-junction solar cell, and in theory you can go 63% efficiency, and this is what I'm trying to explain again. I told you that this is the idea of intermediate band solar cell. You have valence band, because in semiconductor you must have valence band and you must have conduction band, also you must have a band gap in between, okay? But in this idea, you put a IB or intermediate band, okay? In short, IB, I'm going to talk about IB pretty often. If you can put a gap, then now you start to see, oh my God, we have 2 different photon wavelengths. Now they could be absorbed by your semiconductor and they can generate free electron and free hole, and you increase the efficiency. And this is the theoretical calculation I'm showing you here, okay, based on the Shockley-Quasar principle. But they made it on single junction, but the same theoretical thermodynamic principle I'm applying here. And now you see, okay, here is the color contrast, that if you have intermediate band here, and if you change in the horizontal axis, the band gap of your original semiconductor, valence band and conduction band. If you see CV for conduction band, VV for valence band, if you, let's say, increase the band gap in the horizontal axis, and if you play with this intermediate band, that where you want to position intermediate band, on top, middle, bottom, okay, how you can design, because this is, so this is the, you are putting there, that where you put the IV in contrast to conduction band, okay? So so this is the relative position and this is the relative band gap. So if you are switching the IV or changing the IB in between the gap, this is the idea here, that you are changing from 0 to some number. 0 means your IB overlap with the conduction band, and if you increase more and more, okay, you are reducing this, increasing the gap and putting the IB closer to the valence band, and this goes down there, and you make the combinations or all this band gap and do the thermodynamic calculation, and you put them in this color map. Then this blue area tells 10% of solar cell efficiency, conversion efficiency. Red means 70%, close to 70%. If this is the color, and this color tell you that, okay, if you have semiconductor, piece of semiconductor whose band gap is close to 1.9 electron volt, okay, and the intermediate band is close to 0.7 electron volt, and if you can make this kind of piece of semiconductor, then you are pretty close to having a solar cell of 63% theoretical limit. And this is good news, because more than 60% you can convert to electricity, okay? And on your rooftop, the silicon panel, hardly you can go beyond 15% or 16, or if you're lucky, maybe close to 20%. But if you can go 60%, means you can reduce your cost to 1/3, and you can compete the fossil fuels and make solar cell more fabricating more solar cell and generate more electricity out of the sunlight. Okay, so there are different ideas for the intermediate band. I told you that this is the core technology, that then how we can make this intermediate band. There are different ideas, and in our group we have Professor Okada. He's working on this quantum dot solar cell, that you have tiny quantum dot in your solar cell, in a piece of semiconductor, and using the wave function engineering, because in the quantum mechanics, electrons, their wave function, okay? So if you bring small size of quantum dot and you have lattice polarities, play with the wave function engineering, then you can make mini band in quantum dot solar cell. And using the mini band, you can have this kind of intermediate band solar cell structure. Another idea is that I have written here multiband engineering in highly mismatched. For example, gallium arsenide. When I say highly mismatched, means if you if you substitute nitrogen in the gallium arsenide. I mean, you know silicon, but you might not know gallium arsenide. But if you look my pointer, okay, this is my pointer, and this is a red color, I mean, LED laser, I mean LD laser diode. And I think we make this red laser diode out of gallium arsenide. Okay, so my pointer is made gallium arsenide, but here I'm using the pointer of the Microsoft PowerPoint. But in reality, we use gallium arsenide LED. Okay, so that's gallium arsenide, and this is very. We use this material material for optical communications and other things. So, and if you change this arsenic a little bit by nitrogen, okay, this kind of material we call highly mismatched alloy because they are very different in size. Nitrogen is very small atom, and arsenic is big atom. So this mismatch we call highly mismatched. Okay, so and if you do that, you have very interesting electronic structure, and I'm going to talk about that. And you can make intermediate band material. Another idea that copper, gallium, sulfur. This is chalcogenide material. Okay, this is different. And if you put some impurity in this kind of material, you can make impurity band semiconductor. And this is, I have written impurity band engineering. Okay, so today I'm going to talk about this kind of two ideas. Okay, but if you go there, this review paper in 2015, we have all the ideas. Oh, in this paper, maybe we don't see this idea, but we have very similar ideas written in this paper. So in this paper, we have explained different kind of ideas to make intermediate band solar cell. So those who are interested, please check this paper. And this is a review paper, a little bit thick, but we have talked about the thermodynamic calculation and other ideas and how we can implement in different material. So it will give you the first-hand ideas what going and what in the future direction we can. Okay, so this paper tells the recent progress and the future direction in this new ideas of intermediate band solar cell. Okay, so now let me go a little bit deeper. So in a semiconductor, again, because the talk is materials and device engineering, and we make the core silicon solar cell. So we fabricate the semiconductor, we make the device, we characterize the solar cell, and that's how we work. So let me start with, again, the material. So in a silicon material, here I don't assume silicon, but any semiconductor material, you must have valence band and you must have conduction band. And if you have sunlight coming, the sunlight will excite the electron to the conduction band, or in other way, the electron, by absorbing the sunlight, will excite in the higher state, and it will and if you collect this electron as a current, technically you are converting the sunlight into electrical energy. Okay, but now if you have intermediate band in between, okay, then, but if you don't have it, what will happen? Okay, right here. So only this process is possible when you have high energy of photon higher than this band gap. Okay, you see, this is from here to here. I'll talk about this is the band gap. So if you have a photon higher than band gap, only you can excite the electron. But the photons who has energy less than this, okay, then they pass to the semiconductor, which is the case for single junction solar cell. But now we have put some intermediate band. So what will happen? If long wavelength photon cannot escape now, okay, because their energy is now close to this band gap due to the intermediate band, they will be absorbed here. But now you have another set of long wavelength photon. They cannot escape either, because this electron will catch them and be excited and convert to electrical energy. So this is how I'm talking about. This is called 2:1 photon energy, 2:1 photon absorption of the low, okay, long wavelength energy. But I've written but this process, the conversion is low. If you look at there, this is very wide. I've written the width is very broad, but this is very narrow. By this width, I mean the absorption. If you look at there, by this width, okay, but this is very, narrow line. Narrow means less absorption, okay. Wide means high absorption. So if you have narrow absorption, okay, high absorption means most of the photon will be absorbed by, okay, in this gap. Narrow means, okay, few of the photon will be absorbed, but most will be passed through. And in the semiconductor, we have a competing process we call recombination. R for recombination, G for generation. G is the generation because you are generating photoelectron. Recombination is the loss project. Okay, if your electron has a very short lifetime, they cannot move. Okay, they will come back to the ground state and it will be lost as photon. So this is a loss process. Okay, and okay, so this is a, okay, so here we have a bad news that this is a good news that you have many of the photons absorbed, but you have a bad news that the electron going there cannot go to the conduction band. So this electron, unless it goes to the conduction band, you cannot convert to electricity in our concept, in the concept of the intermediate band solar cell. Okay, so you have to improve the absorption coefficient or the width of this line here, and this is the idea. If you look at the width here, it is much more wider if you compare to this, because if you look at there, now we have a lot of electrons. The red state is we have many electrons coming, and this, okay, and here we call half filled. Okay, so more electron coming there and filling the state, the more absorption is going there. So absorption means the electron who can go there. So if you have less amount of electron here, you have less amount of absorption. But here you have many. If you have, okay, more amount of electron, because the dot black means electron and white means hole. So the leftover is the hole, but many electrons sitting. So you have many absorption, and you see very broad absorption here. But if you have less amount of electron, only single electron here, black, so you have less absorption. But you have okay, the red state, many electrons sitting, you have more absorption. So to do that, how we can do that? This is the idea, and we are working on that. So idea is improve, make them broader, and make them thinner, and you can high efficiency solar cell. And when I explain theoretically, I should tell you that, okay, this is the Fermi level. Okay, you know the definition of the Fermi level. Fermi level is the level of the upper position of the electron state. Okay, the electron, the state, okay, which the upper electron fill the state. That's the definition of the electron Fermi level at 0 Kelvin. So here we means our Fermi level is a little bit higher because we have more electrons. So every time I'm not going to talk about this number of the electrons in the intermediate. Technically, I'll talk the Fermi level is high here and Fermi level is low there. Okay, this is how we also calculate. So, and this is how we can do the experiment that our Fermi level is shifting down or up. This is how I'm going to talk. So if sometimes I say Fermi level, then you guys imagine that I'm talking about the Fermi level position of the intermediate band. Okay, so this is a material. This is a material of gallium arsenide. Okay, so if you know the gallium arsenide, I told you that this pointer, okay, made of gallium arsenide PN junction LED. Okay, and why? Because this is a gallium arsenide electronic dispersion of the gallium arsenide material. Okay, so in semiconductor, or you have the valence band, and what exactly is valence band? Valence band is the a band of states of the electron, and for each electron they have different wave number. So here I have written the wave number. I have different electron states. So this dispersion we call a heavy hole dispersion. This dispersion we call light hole dispersion, and this dotted line we call the spin orbital split electrons in the valence band. So this is all about electrons, valence band, and these are the wave number for different electrons. So okay, this is how we draw the dispersion. This is a valence band, and on top this blue one, okay, this is conduction band. So if we excite the electron in gallium arsenide, if the sunlight comes or any light comes, okay, so in solar cell we excite electron from here to there, and you generate the current. But here you see the red LED, LD, okay, or LED, whatever. In that case, it's the opposite. if you put one electron there and this electron guys recombine with another hole here, then same amount of light will be coming out of your LED. So LED and solar cell, exactly the same device, PN junction. This is the opposite. In LED, your input is electrical energy or electric current or electric energy, by the way, and output is light. And in solar cell, your input is light, output is current. So if the same device, okay, it is the same device, okay. So if you're good in solar cell, means you can make a good, in principle, you can make also good LED or LD, okay. Okay, so this is, I'm talking about gallium arsenide, and gallium arsenide is a very popular material in optics, okay. But why I'm talking about gallium arsenide so long? Because this is a single band gap material, and the theoretical limit is only 30%. Okay, if you make a gallium arsenide solar cell, like silicon solar cell, you cannot break the limit of 31%. But if you put a little bit, if you change the arsenic little bit, if you substitute the arsenic by nitrogen, little amount of nitrogen, then very interesting thing happens in the dispersion of the electrons. For example, right now, if you X is 0, means you have no nitrogen. Okay, X means the amount of nitrogen in gallium arsenide. Okay, doping, you are doping. So 0% means 0% is gallium arsenide. This is what exactly. And this is a theoretical calculation, and this is a simulation, because in this simulation I'm changing the nitrogen concentration. Okay, and this is 0%. Now let me start my simulation. But I think it will not work if I don't change my pointer. I have some trouble. Okay, I think it will work now. Now this is 0%. Okay, good. What I'm doing now, I have put this X to 0.7%, 0.7%. Okay, and if you more, okay, oh no, stop there. Let's say 2%. So what I'm doing here, I have out of 100 arsenic atom, I am substituting only 2% of the nitrogen. Okay, and rest 98% arsenic is there. So your original semiconductor is gallium arsenic. I am just substituting 2%, or let's say 2.9%, okay, or 3%, okay. So this simulation is from 0 to 3%, but within the 0 to 3%, this shows very interesting. If you look more and more, you see valence band is doing nothing. Everything happening in the conduction band. For example, this is 1.8%, okay, in gallium nitride arsenide. And now if you look at there, now this is original conduction band of your gallium arsenide, but now in this new material you have a new band. This is the red band, and also you have second band. This is the blue band. Okay, and interesting thing, the more amount of nitrogen you are putting, the more these guys go down and these guys go up. Okay, again let me show. So this is the idea. This is okay. This is the idea that we can make a single band gap into triple band gap. Okay. So now you see we have the the first band gap. From here to there we have the second band gap, and from here to there we have the third band gap. So by using a single amount of nitrogen, just single atom, we are working with 3 band gaps. Okay, and there are the numbers of the band gap. For the red one, you see, for 2% of nitrogen, the lower band gap. Okay, let me go start from the very beginning. Oh no. Okay, so at 0%, my original band gap was 1.4 electron volt. Okay, but for 3% now the band gap, red band gap is okay. Let's say 1.06 electron volt, and the largest band gap is 2.02 electron volt, and this band gap should be 2.02 minus 1.06. Okay, so this is okay. Now if you bring your solar sunlight, now this sunlight long short wavelength photons will be absorbed from here to there, and long wavelength photons should be absorbed either from here to there or from here to there. So this is very close to a 3-junction solar cell. And now this is, I'm talking about the band gap. Now here, okay, let me go here. Pointer. Now right here, what I'm doing In the horizontal axis, I'm changing the same nitrogen concentration, okay, 0% to 3%, okay, 2.5% here. And in the vertical axis, I told you very beginning that we can concentrate the sunlight, okay, and gallium arsenide is very expensive material. At the same time, this kind of material, okay, theoretically, if you concentrate the sunlight, you can increase the solar cell efficiency. So we do have dual effect. So what I'm doing, I'm concentrating the sunlight from one sun. One sun means no concentration because it's just single sun, one sun we have on top of head. But if you concentrate 10 times here, 100 times here, 1,000 times here, 10,000 times here, this is log scale. And this is my picture, and this color tells the conversion efficiency. So if you have 0%, means you are very close to the green area, and green area means somewhere 30%. Okay, but if you increase the nitrogen concentration, let's say 1%, okay, or then you do have 3 band gap like this, and in that case, under one sun, your solar cell efficiency will be close to 40%. But for example, if you here and if you increase the solar concentration, go higher and higher and higher and higher, and the highest is red area, and the red area here, then you can make solar cell 63%. So this number is very close to 1% of nitrogen there, and under concentration of 10,000 times. Okay, so this is the benefit of concentration. Okay, if you don't concentrate it, your solar cell, just put it there on rooftop and measure, will be somewhere here. But if you have some good let's say magnifying glass and concentrate the sunlight, then your solar cell conversion efficiency will go higher and higher. Okay, and you go 63%. Okay, and this is a DFT calculation, density functional theory calculation, with the same material. And I'm talking about that I'm playing with the Fermi level, or technically I'm playing with the absorption coefficient with the band gap, and I'm trying to, by playing these are the Fermi level. Okay, if you dope more and more, okay, then you can shift your Fermi level and you can play with the absorption coefficient of your material. And I told you, one of the slides that you have to match the absorption coefficient. Okay, if one absorption coefficient is very wide, another guy is very thin, there is a mismatch, then okay, you cannot bring the maximum potential. The maximum potential is that through your intermediate band, the number of electron exciting should to the intermediate band should be excited again by another photon to the conduction band, and if they absorb in the similar amount, then you have the highest conversion efficiency. So here your Fermi level is not well matched, but here you are shifting the Fermi level from original position, and we are calculating the absorption coefficient, and we show that okay, we can play with the absorption coefficient by first principle calculation. And this is the experiment that it tells that in gallium arsenide, if you dope, this is experimental, we have grown single crystalline high quality gallium arsenide nitride material on gallium arsenide substrate. Okay, we call this heteroepitaxy. You have high quality material, and we really want to check that if we do have 2 band gaps. So this is we call photoreflectance spectra, and in the between right here, I told you that gallium arsenide has a band gap of 1.42 electron volt, and this signals coming from the photoreflectance. Okay, so that this signals coming from your substrate. So this is a reference. But if you see that from your material of the thin film on top of the substrate, we have a low band gap material. If you go down and down, this is the photon energy, but it also tells that this is the band gap. These all tell your band gap. Okay, whatever feature you see tells that we do have a band gap. So here in all our material, it tells that we have 3 band gap, but the middle band gap comes from the substrate. Now this is a low band gap, so the more amount of nitrogen, so you put more amount of nitrogen, more go higher and higher. Here I have shifted the graph in the same graph. Okay, it is difficult to understand, but I'm shifting one after another because I have different set of thin film, and I want to show you on the same graph. So difficult to understand, but just imagine I have measured 1, 2, 3, 4, 5, 6, 3, 8 samples, and I'm overlapping them. But one thing, if you increase more and more amount of nitrogen, you are playing with the lower band gap, you are reducing the band gap here. And your higher band gap going up and up and up. And the same thing for my eye, I redraw here that if I put nitrogen composition in the horizontal axis and I redraw the lower band gap here and the upper band gap there, and I plot the model diagram, theoretical calculation on top, I see that the experimental data I can explain by theoretical theoretical function, and the experimental data good match with the experiment. And the message here that if you change the nitrogen concentration, you can play with triple band gap. Okay, this is the idea here I'm showing. Then the question comes, okay, now you have the material, and okay, you have intermediate band, but are you sure that you do have 2 photon absorption? Because this is a very important question, because you might have an intermediate band in any material, but it doesn't guarantee you that you must have 2 photon absorption, because photon absorption is a quantum mechanical process, and for semiconductor you need a direct band gap for that. And that's why silicon is not good for photonic device, because it doesn't have a band gap. So to do that, we do have 2 photon absorption setup, that you put 2 long wavelength photon, and you make sure out of the 2 photon you can generate 1 pair of electron on hole. Okay, so we do have this kind of setup, and this is the first paper we demonstrated that, look, using this material we demonstrated the room temperature the first demonstration of the room temperature 2 photon absorption in this material. Okay, and we have 2 photon here. Okay, if I think, does it? Okay, so here I have 2 photons, 1 photon coming from 1 light source, another photon coming from another light source, and I have a solar cell here. And out of the solar cell, I compare that, look, we can generate photocurrent due to a 2 photon absorption. So we in our laboratory, this is we must do this experiment to claim that our material can be utilized in a solar cell. Okay, and this is the another paper in 2013 that that we show that indeed we demonstrate the 2 photon absorption due to the intermediate band. And here the wavelength is the wavelength coming from the sunlight, and the vertical axis, this delta QE, it tells the amount of the long wavelength photon you can convert to electrical current. Okay, so if it is 0, so means you're in, okay, so you see dotted line. So we confirm that if you don't have intermediate band, you cannot convert 2 photon absorption and you don't get any electric current. But if you have intermediate band in this kind of solar cell, then you can generate twist current due to 2 photon absorption. And this sample we made by molecular beam epitaxy on gallium arsenide solar cell, on gallium arsenide substrate. Okay, for example, here I have an N-type gallium arsenide substrate, and there I have a gallium arsenide buffer, and then I have a aluminum gallium arsenide wide bandgap barrier layer. Then I have a material gallium nitride arsenide intermediate band material. Then I have another P-type wide bandgap material, and then I have a window layer. So you know, I told you the semiconductor solar cells are sandwich of p-n junction. So we have p-n junction backside and foreside, but in between we have intermediate band material. And this kind of material, okay, we have demonstrated that we can generate the current due to 2 photon absorption. And due to time, I'm gonna let me go. If you have question, please ask me later. Let me, I'm a little bit lagging behind in my talk, so let me continue. But here, the message here is that if you look at the blue line, this is gallium, this is the material based on gallium nitride arsenide. But if you look at, they are only 0.5% we can make only 0.5% of the the efficiency is very low. I mean, the twistor photon absorption is the long wavelength photons. We can convert only 0.5% of them to electric current. But here, this is one of the reasons this material, due to nitrogen is a very difficult atom in gallium arsenide, okay? We generate a lot of defects. And we demonstrate here that if you put a little bigger amount of antimony, then you can improve the material quality. And due to that, you can increase the conversion efficiency from 0.5 to let's say close to 1.3%. So we have to work with the material quality. But the key concept here that we have demonstrated for the first time that, look, we can play with the intermediate band gap material and also make them work as a solar cell. And this is the process I'm talking about in details, okay, here. So if you have interest, please check this paper I have written here. Okay, so so far I'm talking about one idea of gallium arsenide nitride based on molecular beam epitaxy. And we are also working on different kind of material. Let me introduce another kind of material, copper gallium sulfur. And okay, let me work on this. Okay, so this is a DFT calculation, first principle calculation. I mean, DFT means density functional calculation. And this is DFT calculation that I show you here, that in copper gallium arsenide, this is, if you have copper gallium arsenide, and if you draw the dispersion of the electron, then we see that there is a band gap. And this is the band gap. And this is a semiconductor. And if the band gap is the same location, we call them direct band gap material. So this is a good news. And very, very good news is that they have a high absorption coefficient. Okay, but now in CGS, you substitute the gallium atom by a little bit chromium atom. Now the situation changes. Now you see things have changed. And now in this calculation, suddenly we see we have new two state coming very close to the Fermi level. Zero means the Fermi level, okay? And now the good news here that now we have three band gap. Here we have one band gap, but if you see there, this is the Fermi level. Around the Fermi level, we have now three band gap. I'm sorry. The first band gap is here, and second band gap here, and third band gap here to there. So this is, I call the impurity dope material. We call impurity dope material, but but the point is, by impurity doping, you can also make intermediate band material. And okay, so this data, we talked about this in 2017 in Washington, D.C. in the conference of PBSC. And now we are calculating different kind of material, okay? Not only chromium, okay? This is the CGS material, okay? You have a single band gap. If you substitute the gallium, so we are substituting the gallium by different dopant, and we are doing the calculation. And you see, for some kind of, this is chromium. Let's say this is gold, not gold, sorry, iron. This is cobalt, nickel, and we have different kind of calculation. I'm just showing you for you to get the idea. Only very selected of material that, look, by doping, we can play with the band gap. And we can make them multiple band gap material, okay? And we can utilize them for intermediate band gap solar cell structure, okay? And again, I'm showing you here that's copper gallium sulfur. This is the absorption coefficient, okay? And you see that just around the band gap, it has a very sharp rise of the absorption coefficient. So it tells you this is a direct band gap material. And this is very important that this absorption should be very, very high right at the band gap. Then you can make thin film solar cell. And this is the idea of thin film solar cell, second generation solar cell. That if you have a very high absorption coefficient just right at the band edge, and then you can make thin solar cell. And this is but now if you dope your copper gallium sulfur gallium by a little bit chromium, now you see that you have three band gaps. This is the again calculation, okay, and all of them show very rapid rise in the absorption coefficient. So means that, okay, and they have very similar strength, okay, of the absorption coefficient. They're very similar. So it tells that you have, for the twist of photon absorption, your absorption should be matched, okay, to make the most of the photon to electrical conversion. And this is a very good news. Then this is our calculation. Then we started characterizing the materials, and okay, XRD characterization tells, look, we can make a smaller grain. These are made, by the way, by sputtering, not molecular beam epitaxy. These are made by sputtering, but we can have some. This is some that this is just in sputtering, made sputtering. But if you sulfur anneal them, then you see that smaller grain is becoming bigger and bigger. And the bigger grain means that the photoelectron lifetime will be very good, and you can have high solar cell efficiency. And this kind of material is very tricky because sulfur, the vapor pressure is very high, okay, and very tricky to make in sputtering. So we are working with we spend most of our time in designing the sputtering system, having co-deposition sputtering with multiple guns, co-deposit them, and how. So one of our main challenge, how we can make high quality CGS just inside your CGS without breaking the let's say vacuum environment. So our target is to make the sulfurization, everything, all the process inside the vacuum. Okay, most of the CGS technology current day is you make the thin film, okay, and then bring the vacuum, bring the sample outside the chamber, do sulfurization. If you do that, good thing, you have work, you have more freedom. But the bad thing, once if you expose your high quality material in the air, then you have to compromise the interface quality. And in solar cell, it is very important that you don't put a defect in your interface, okay, and make your interface high quality. And to do that, if you can somehow make all your process inside vacuum environment, that give you less amount, defects. And that's why we are optimizing our sputtering system. So here I show you that if you have less sulfur, then your bandages, you see, go shallow and very slow rise, and it tells that your quality is not good. You have lot of states down the conduction band, and you don't have a good band gap. But if you have sulfurization with your thin film, then the band gap becomes sharper and sharper, and then you have more least amount of bandage defects inside the bandage. And so right now we are playing how we can reduce the amount of the states below the band gap and make the band gap sharper. Okay, and this tells photoluminescence. Photoluminescence out of this two set of copper gallium sulfur thin film, that if you do sulfurization, you have high photoluminescence, but if your material quality is compromised, then you have a very broad photoluminescence. So you are still working with the materials, okay, and okay, I have very limited time. I'm giving just 1 hour and a half, I think. So today's talk was materials and device engineering. So the last part was actually device, because we do have lithography and device and many things we do with our samples. So I think I'll be very fast. Within few minutes, I'm going to stop this part. And okay, so here, the main challenge when you make your material into a device, the main challenge is in your intermediate band, the electron, if you can excite the electron intermediate band, the electrons, okay, can escape to the contact directly. So there are different kind of pathway of the intermediate band. The best, what we expect is the process one, that you excite the electron by some long wavelength to the conduction band. But what exactly happens most of the time, that this guy, before going there, it tunnel through to the conduction band. This is called tunneling loss. Another process, if your band, okay, if this gap is narrow, that before exciting the electron by the light to the one process by the heat, there is, okay, you have thermal escape of the electron. That is also another layer. So 2 and 3, we don't expect, okay. So this pathway, this is the pathway we expect, but most often we end up with 2 and 3 because these are fast process. And to avoid this, we do different kind of engineering with our material, with our device, and we do have some simulation of the device, and we do the device simulation before fabricating the real solar cell. So these are the device simulation of our valence band, intermediate band, conduction band, okay, by drift and diffusion. And we, okay, so we are doing the simulations here. And the horizontal axis is the distance from the surface of your PN junction. And the vertical is the energy. And this is the band diagram. But this is very, very important to see what go through your materials, okay? So this is not under the sunlight. This is at dark. Okay, so we design, and okay, so the next slide. Okay, so I'm gonna show, let's say if you dope your intermediate, so okay, so you have a high band gap barrier here. If you change the doping concentration, so if your doping is high, let's say 4 times 10 to the power 17 in the barrier, then you have a very thin barrier here. Most of the electron can pass through this, through tunneling here. So before going there, it can pass through. To avoid that, maybe you reduce the doping concentration, which is the next slide, that you reduce the doping concentration in the barrier to 1 order. Then now the width is so long that this electron, it says, oh my God, this barrier is too deep. So let me wait here for the second photon, then let me go higher. So this is how we design the doping profile in, okay. And if you have less amount of doping, then, okay, you see the electron right here who go there, still they say, oh my, this is too thick. So let me wait right here for the second photon and keep quiet and wait for the 2:1 photon absorption. So it tells that if you have a low amount of electron concentration in your barrier, that can stop the electron tunneling and improve the 2:1 photon absorption. This is how we design the device. Okay, so this is the total summary, that if you have different doping profile in your barrier, okay, for the third, you see, if you have a high concentration, then electron tunneling will be high. But if you have low and lower concentration, you can reduce the electron tunneling. Then you left with 2 options, either photon absorption or thermal escape. So if you higher the band gap, then you can reduce the thermal escape and only left over with 1. So in your gallium nitride arsenide, at the very beginning, I told you, if you change the nitrogen concentration, you can play with the band gap and also play with this process 1 and 2, and you can optimize your device. This is the device engineering, okay? And then you make your okay. This is how we are designing our gallium nitride arsenide as antimonide, and we are changing. And this is the real semiconductor, okay, real solar cell. That if you have a high doping in your the blue, the red, black one is the high doping barrier, then you have a very low open circuit voltage. But if you reduce the doping concentration, you are increasing the open circuit voltage, and the more voltage you can gain if you have least amount of doping in your barrier. And we have so this is how we design, and experimentally we demonstrate that our design also work in real system. And we also demonstrate by designing we can play with the current generating by the photon. And so this is the idea, experiment and design I'm showing you here. And let me summarize here. I am taking most of the time, my talk. That let me talk. So in the very beginning, I talk about the different material systems we can work. I introduce with different kind of materials at the very beginning. For the idea I introduced today, we need 2:1 photon absorption for the intermediate band solar cell, and this is the key idea. And I also talk about the density functional calculation of some of the material, including CGS or gallium nitride arsenide. And I also introduce some of the material, molecular beam epitaxy, synthesis, characterization. And I also talk about device engineering, how you play with your device and you demonstrate it in experiment. So with that, let me finish my talk, 1 hour and 30 minutes talk. And let me conclude here. So these are the groups and the funding agencies. So I'm gonna acknowledge Professor Yoshitaka Okada. He is he's the pioneer in this field, and I introduced that we have a paper in this intermediate bandgap solar cell material in the beginning. And then we have another group in Lawrence Berkeley National Lab in the United States. So there we do the theoretical ideas and some of the characterization of the materials. And also you have another group in the City University of Hong Kong, Professor Kim Man-yu. He was actually in the Lawrence Berkeley National Lab, long days, right now he's there. And then I have another professor, S. Kalainathan in VIT University in India. And in fact, so these are the funding agency, but I want to highlight Professor Kalainathan here because he's from India. And we have GSPS bilateral DST, GSPS DST bilateral collaboration. And some of the CGS characterization things we did together. So for the sputtering and other things, okay. And so I want to acknowledge the NATO, US Department of Energy, GSPS, DST bilateral collaboration, and GSPS Kakeni for this talk. With this, I want to end my talk. Thank you very much for listening so long time. So now open for question.
Dear participants, you can question directly, or else you can post it in the chat box.
I'm sorry, this is first time I'm using Google. Can you help me how I can see the chat? Okay, so if you help me, actually I always use Zoom. This is the first time I'm using Google. So I'm sorry if I cannot see it.
Okay, sir, the first question is, why multi-junction solar panels are not available in the market for power generation?
Okay, so, okay, thank you very much. Let me show again. Okay, and I'm sorry. Okay. So I should, yeah, this is very important question because I told you that, I cannot go. Yeah, so let me go back. So, yeah, so the multi-junction solar cell, for example, this is the requirement for multi-junction solar cell is very, technologically challenging and financially expensive. For example, the gallium arsenide wafer, for LED, you use a couple of millimeter phi. Okay, so LED is very for laser diode fine. You can make LED, but solar cell you need large area, and compound semiconductor is very expensive, very expensive. They're good for photonic device in terms of cost, but when it comes to solar cell, you need large area. So cost is the main trouble. Okay. And so it's all about cost, that you cannot reduce the cost. Then you can ask me why it's still expensive. It's not only material. Most expensive is the procedure. For example, we use molecular epitaxy for this kind of material, and these are very challenging to make lattice matching because different semiconductor has different band gaps or different lattice constant. And if you have a mismatch in the lattice, materials have lattice constant, different atoms, ordering atoms. So different material has different ordering. So if you put one material on top of another material, in the interface, they have a strain. And this strain change the ordering and bring a lot of defects. And those defects reduce the open circuit voltage and the current because now you have defect. These defects work as trap, and they trap down the photon. So you have reduced photocurrent, you have reduced open circuit voltage. So it's not only about cost, okay? It's also about technology, technically cost again. that to make high quality, you have to employ high level of technologies. And that's why in my beginning slide, you'll see that multi-junction solar cell hardly started in 2000. Because right there in the 1990s or 80s, the molecular beam epitaxy, okay, people got Nobel Prize right here due to high mobility transistor or high mobility whatever, and these are possible due to molecular beam epitaxy right in 1980s to 2000. Okay, people got a couple of Nobel Prize for fractional quantum Hall effect, high mobility transistor, and so many things. And since 2000 now, the same technology people started employing for, let's say, multi-junction, because now they can make high quality material. Now they can make lattice match using these technologies, okay? So these all made this solar cell very expensive. And this is why we need to bring new ideas, okay? Okay.
The next question is, which is best solar technology available in market for experimental purpose?
Okay, so so it depends what kind of experiment you want to do, okay? Because different people have different experimental setups. So if somebody want to work on concentration photovoltaics, that let's say he want to reduce the cost, then then what he can do, maybe he can contact some of the companies I've written here and buy expensive multi-junction, but he can have his own CPV where he can concentrate the sunlight, then he can do this concentrated experiment, okay? But the question is cost effective, I think, that for the experiment. So it depends what kind of experiment he want to do. So, if you want to reduce the cost, of course, you should not choose this area. You should go, for example, you can, for example, this quantum dot cells, the emerging PV, these are chemical process, liquid process. You can buy quantum dot, the liquid, bottle. So in terms of the cost, you can buy this kind of, let's say, cadmium sulfide dot or whatever, and make chemical processing. But if you do chemical processing, you are compromising your efficiency. But only exception is perovskite, okay? Perovskite is different. It is using mostly chemical process. But here, you see, not stable a lot. So in this chart, it is written in bracket, not stabilized. It has its own problem, but perovskite is the only exception which made people, okay? So if you want to, thinking cost effective, maybe perovskite solar cell is it is high efficiency, but you can start with low efficiency. But so a lot of people working in this field, okay? So I think, it's very subjective question. It depends what kind of experiment you want to do, okay? I hope it helps.
Participants, any other questions, please? So hope there is no questions. So thank you, sir, on behalf of Department of Mechanical Engineering, Jyoti Engineering College. So my gratitude to Professor for spending his valuable time here. So in spite of his busy schedule, he has delivered the wonderful, very interesting and informative. So because we all know that there is different timings in India as well as Japan. So whenever I continuously messaging him, I will get a message delay because of his timing. So I was worried about when he will be available on time or any other some slight changes will be there or not. But really he came in exact time what we have mentioned in our schedule. So thank you very much, Professor, for your valuable information and sessions which. So
Thank
and
you.
also here I would like to thank Dr. Ranjita for introducing Professor to me, because she only introduced Professor to me program. So I take this opportunity to thank her here in this stage. So we expect that our professor session we can have in future events, because since this is a 1.5 hour session, so he not delivered the exact content what he planned, because we took some more time, but because of our time limits for another sessions and all, we limited to 1.5 hours. So professor, we are sure that in future we will give you more time for you, and we are expecting for your sessions in the upcoming days.
Thank you so much.
Yeah,
Thank you
thank you.
very much.